It's kind of mind-blowing how fast the world of large language models is moving, isn't it?
Absolutely.
I mean, just in 2024, we've seen these incredible leaps with models like GPT-4o, Llama 3, Cloud 3.5 Sonnet, Grok 2, Qwen 2.5, Gemini 2, DeepSeek V3.
The list just keeps growing.
Right. And the trend seems clear. Bigger often means, well, smarter, more intelligent. But, as they get more powerful, there's this huge hurdle.
Getting them to run efficiently.
Exactly. Especially the ones doing complex reasoning, handling massive amounts of information, using them affordably and quickly.
That's really the central challenge, isn't it? Building these giant AI brains is one thing. Getting them to operate swiftly and cost-effectively is, well, something else entirely. And that's precisely where our focus is today.
Perfect. So we're doing a deep dive into the research behind DeepSeek V3. We're pulling insights directly from their paper.
Yep, the source material itself.
Think of this as like your fast track to understanding how this model pulls off both high performance and surprising cost effectiveness, both for training and for actually running it at scale. Our mission here is to break down the really ingenious ways DeepSeek V3's design works with the hardware it runs on. It anticipates the limits.
It's all about that interplay.
Exactly. The dance between the AI model and the silicon. We want to uncover some, genuinely surprising facts without getting totally lost in the weeds of technical jargon. Okay, let's unpack this.
So the core idea, the real heart of DeepSeek V3 is what you could call hardware-aware model co-design.
Hardware-aware co-design.
Okay. It wasn't just about making the model bigger. It was about designing it from the ground up, being deeply conscious of the capabilities and maybe even more importantly, the limitations of the hardware.
The specific hardware they used for training and running it.
Precisely. In their case, that meant a pretty beefy cluster, 2048 NVIDIA H800 GPUs.
Okay, 2048 H800s. And one of the key innovations that came out of thinking hardware first is something called Multi-head Latent Attention, MLA.
That's right.
Now that sounds, well, technical, but the basic idea is really smart for saving memory, isn't it?
Oh, absolutely. Memory usage is a massive bottleneck for these huge LLMs.
Right.
And the demand for memory is actually growing much faster than the capacity of high-speed memory, like HBM, is improving.
So we need tricks.
We need tricks. And MLA is a clever one. It directly tackles this by compressing the key value caches, the KV caches.
Okay, the KV cache. Remind us what that is again.
Think of it as the model's short-term working memory when it's generating text or answering a question.
Got it.
Instead of storing, all the detailed context for every single step across all its attention mechanisms, MLA kind of distills this information. It compresses it into a much, much smaller, latent representation.
So like you said, it's making a super condensed summary of the key stuff instead of keeping every single note. That makes a lot of sense.
Exactly.
The paper also mentions other ways people try to shrink that KV cache, right?
Right.
Like shared KV. GQA, MQA, and windowed KV.
Yeah, those are other common techniques. Shared KV approaches like grouped query attention or multi-query attention save memory by having several attention heads basically share one set of keys and values.
Okay.
It works, it saves memory, but sometimes it can slightly limit how precisely the model can focus on different nuances in the input.
That trade-off.
A trade-off, yeah. And windowed KV is simpler. It just keeps the KV cache for the most recent, say, few thousand tokens, a window.
Which saves memory but might hurt its ability to remember things from way earlier in a long conversation.
Exactly. If you need that long context reasoning, windowing can be a problem. But what's really striking with DeepSeek V3's MLA is just how much they reduce the cache size.
Okay, how much?
They get it down to about 70 kilobytes per token. 70 KB.
70, wow. Compared to what?
Well, compare that to models using GQA like Qwen 2.572b that needs about 327 KB per token, and Llama 3.1405b needs a whopping 516 KB.
Whoa, so 70 versus like 300 or 500. That's a massive saving in memory.
It's a game changer for memory footprint, especially during inference with long contexts.
Okay, memory efficiency check. What about the other big resource hog? The sheer computational cost. That must be enormous for these models.
Oh, definitely. And that's where the second big architectural piece comes in. Mixture of experts. MOE.
MOE, right. We hear that term a lot.
And for good reason. The core idea with MOE is to slash the computational work needed, especially during training, but also inference.
How does it do that?
Instead of making the entire massive model crunch numbers for every single input token.
That sounds incredibly expensive.
It is. MOE only activates a small fraction of the model's parameters, these specialized subnetworks called experts for each token.
So it's like having a huge team of specialists, But for any given problem, you only call in the 2 or 3 most relevant experts.
That's a great analogy, exactly.
So how does that look in DeepSeek v3 specifically? How big is it, and how many experts get called?
Well, DeepSeek v3 is enormous overall, 671 billion parameters in total.
671 billion.
But, and this is the key, only about 37 billion of those are active for any single token that passes through.
Okay, 37 billion active out of 671 billion. How does that compare?
Well, their previous model, DeepSeek v2, was 236 billion total, 21 billion active. And compare it to dense models, where all parameters are always active. Think Qwen 2.572b or Llama 3.1405b. All 72 billion or 405 billion parameters fire for every token.
Right, so computational savings must be huge.
They really are. The paper quantifies it. DeepSeek v3's training cost is around 250 gigaflops per token.
Okay.
Qwen 72b needs 394. And Llama 405b, a massive 2,448 gigaflops per token.
Wow, nearly 10 times more than DeepSeek v3 in that case. That's incredible.
It really highlights the efficiency MOE brings to the table for training these monsters.
And the paper also mentioned MOE being good for personal use or running models privately?
Absolutely, because only that smaller fraction of parameters is active during inference too. The memory requirements and the computational load are much, much lower than a dense model of comparable total size.
Makes sense.
They gave an example. DeepSeek v2 could hit nearly 20 tokens per second on specialized AI chips, system-on-a-chip devices.
Pretty fast for edge hardware.
Yeah, and even the full DeepSeek v3 model, the big 671b one, can apparently run on a server with a decent consumer GPU.
Really? Like something you could actually build yourself?
Potentially, yeah, especially with optimized inference engines like K-transformers they mentioned, and still get speeds around 20 tokens per second. This really lowers the barrier to entry.
That is huge for making these powerful models more accessible, not just locked away in giant data centers.
Exactly. It's about democratizing access.
Okay, so MLA for memory, MOE for compute. What else? They also use something called FP8 mixed precision training. What's that about?
Right, FP8. That stands for 8-bit floating point. It's basically using numbers with lower precision compared to the standard 16-bit or 32-bit formats.
Lower precision means less accurate?
Potentially, but they use a mixed precision strategy. They carefully figure out where they can use these less precise FP8 numbers without significantly hurting the model's final quality.
Okay, and the benefit is?
Big savings. Lower precision means less memory needed to store the numbers, and crucially, the computations themselves are much faster on hardware like the H800 tensor cores, which are optimized for these lower precisions. It makes training these huge models much more practical and cheaper.
And DeepSeek v3 was special in using this.
They state they're the first open-source large model to publicly detail using FP8 for training. They even open-source their optimized library for it, called DeepGEM, and they use a clever, fine-grained approach applying quantization differently to activations versus weights to maximize the benefit. It's about making the basic math operations faster and lighter.
Super low-level optimization then. Okay, one more architectural bet. The Multi-Plane Network Topology, MPFT, what problem is that solving?
MPFT tackles the infrastructure cost specifically, the massive, expensive network needed to connect all those thousands of GPUs together in the training cluster.
Right, linking 2048 GPUs isn't trivial.
Not at all. Instead of a standard, often complex and costly 3-layer fat tree network, they implemented this multi-plane topology. It's essentially a more streamlined way to handle the communication traffic between GPUs, aiming to reduce the overall networking hardware cost.
So smart's not just in the model code, but in the physical network layout too. Very holistic.
That's the co-design principle in action.
Okay, so they built this efficient model with the hardware in mind. But the paper also goes into the challenges they hit with the hardware and has suggestions for the future. What stood out to you there?
Yeah, that part was really insightful. With FP8, for example, while it's great, they noted limitations. One is the restricted accumulation precision in the NVIDIA Hopper tensor cores.
Accumulation precision.
When you're doing lots of calculations, you add up intermediate results. The Hopper hardware has a limit on how precisely it can store that running total when using FP8.
So tiny errors could potentially build up.
Potentially, yeah. So they suggest future hardware should increase this precision, maybe even make it configurable. They also mention the computational overhead needed just to handle the scaling factors for their fine-grained FP8 quantization.
The extra math to make FP8 work well.
Right. And they argue this should ideally be handled directly by the hardware native support. They point to NVIDIA's newer Blackwell architecture and its microscaling format as a good step in that direction.
Makes sense. Build the optimizations right into the silicon. Now, they also talked about something called log FMT for compressing data during communication, but they didn't end up using it. Why not?
Log FMT, yeah, that was interesting. It's a novel logarithmic floating point format. The idea is it might distribute the values of activations more evenly and handle a wider dynamic range.
Sounds potentially useful.
And their early tests on dense models actually looked good. It even beat FT8 accuracy at the same bit width.
So what was the catch?
The current GPUs just weren't quite ready for it, especially in the context of MoE. The math involved the logarithms and exponentials chewed up too much bandwidth.
And encoding, decoding it put too much pressure on the GPU's registers, especially during the intense all-to-all communication needed for MoE. It actually slowed things down significantly, like 50 to 100% overhead in some cases.
Oh, so a cool idea, but the hardware couldn't efficiently execute it yet.
Exactly. A case of software ideas maybe being slightly ahead of the hardware implementation.
And did they suggest a hardware fix for that too?
They did. They proposed that future hardware could include dedicated compression and decompression units, specifically designed for formats like FP8, or custom ones like log FMT, right on the network interface or within the DPU itself, that would offload the main compute cores and slash the bandwidth needed.
More specialized hardware functions. Okay, now the DeepSeek V3 cluster used H800 GPUs. Did that specific chip influence their choices? Any quirks?
Yes, definitely. The H800, compared to its sibling, the H100, actually has lower bandwidth on NVLink.
NVLink being the super fast connection between GPUs inside a single server box. Correct. So with less speed inside the box, they had to compensate between the boxes. Each H800 node in their cluster was kitted out with 8 high-speed 400 gigabit InfiniBand network cards NICs. 8 NICs per node.
8. Okay, so they leaned heavily on the external network.
They had to. It shifted their optimization focus towards making internode communication incredibly efficient, rather than relying as much on intranode speed.
And I guess that directly shaped how they parallelized the training.
Absolutely. Because that intranode NVLink was comparatively weaker, they basically avoided using tensor parallelism during training.
Which relies heavily on that fast NVLink.
Exactly. Instead, they focus on pipeline parallelism. They call their version dual pipe, which is better at overlapping computation with that slower internode communication. And critically, they made heavy use of expert parallelism, leveraging those 8 InfiniBand NICs per node for super fast all-to-all communication between the MoE experts spread across the cluster. They even open-sourced their library for this DPET.
Okay, so the hardware limits directly forced specific parallel strategies. They also mentioned node-limited routing for the MoE experts. How does that fit?
That's another really clever piece of co-design, linking the MoE logic to the network reality.
Okay.
It directly addresses that difference in speed-faster NVLink inside a node, slower InfiniBand between nodes. They grouped their MoE experts. I think they had 256 routed experts in total.
Right.
And they designed the routing logic so that any given token would only be sent to experts located on a small number of other nodes. In their example, a maximum of 4 out of the 8 nodes in a group.
So it tries to keep the communication local as much as possible.
Precisely. By limiting how many distinct nodes a token needs to talk to, they maximize the chance that the required communication happens over the faster intranode NVLink, and they minimize the traffic hitting the internode InfiniBand bottleneck.
Like setting up regional communication hubs instead of everyone shouting across the country. Very smart.
It's all about managing that bandwidth hierarchy.
The paper also talks about challenges where scaling up within a server and scaling out across servers meet. What's the issue there?
A key bottleneck they identified is that during training, the GPU's main processing units, the streaming multiprocessors or SMs, actually get involved in managing the communication traffic.
The processors are doing networking chores.
Yeah, things like forwarding data between the InfiniBand network and the NVLink network, handling memory layouts, converting data types. It all consumes computational cycles on the SMs. They said up to 20 SMs on an H800 could be busy just doing communication tasks during training.
Taking away from actual model computation.
Exactly. Interestingly, for online inference, they use a different approach using the NIC's own RDMA capability for the expert communication, which bypasses the SMs and avoids that contention.
Which shows the benefit of offloading that work. And the paper suggests ways future hardware could bridge this scale-up, scare-out gap more smoothly.
Yes, quite a few ideas. Things like unified network adapters, maybe built into an I/O die that handle both internal and external networks, maybe even with basic switching built in.
Like a universal translator for networks.
Kind of. Also, dedicated communication coprocessors, again, maybe on an I/O die, to handle all the packet processing and memory copies, freeing up the main GPU cores.
More specialized hardware.
And flexible hardware support for common communication patterns like broadcasting or reducing data across both network types, plus better hardware mechanisms for synchronizing things efficiently, maybe using memory semantic communication. They mention emerging standards like UEC, UA-Link, and UB as potentially heading in this direction.
Sounds like a push towards much more integrated and communication-aware hardware designs.
Yeah.
They also brought up bandwidth, contention, and latency.
Yeah, another current hardware pain point. Right now, there isn't really a good way to dynamically manage or prioritize different kinds of traffic sharing the same links, like NVLink or especially PCIe.
Give me an example.
Okay, during inference, you often need to load the KV cache, that working memory we talked about, from regular CPU RAM onto the GPU over the PCIe bus.
Right.
That transfer can totally saturate the PCIe link. Now, if at the same time the GPU is trying to communicate with other nodes for expert parallelism using InfiniBand NECs, which also connect via PCIe.
Collide. Bottleneck.
Exactly. The KV cache transfer hogs the PCIe bandwidth, starving the network communication, leading to performance drops and unpredictable latency spikes.
Like a traffic jam on the data highway. What's the proposed fix?
Well, first, being able to dynamically prioritize traffic, telling the system, hey, this network traffic is more critical right now than this memory transfer, or vice versa.
Smart traffic management.
And second, a more radical idea, integrate the NICs directly into the GPU package, connecting via an internal high-speed fabric on an I/O die instead of going out over PCIe.
Get rid of the PCIe bottleneck for the NICs entirely.
Precisely. That would slash latency and eliminate that specific contention point. They also suggest connecting CPUs and GPUs within a server using NVLink or similar fabrics, not just PCIe.
Again, tighter integration seems to be the theme. Let's circle back to that network they actually built, the Multi-Plane Fat Tree, MPFT. Can you break that down a bit more?
Sure. So imagine the typical network switches connecting all the GPUs. A standard fat tree can have multiple layers of switches. Their MPFT is a two-layer design. The key idea is that each GPU and its associated NIC are assigned to a specific, distinct plane within this network structure.
Like parallel universes for data packets.
Sort of. They had these distinct planes using their high-speed InfiniBand switches, plus a totally separate Ethernet network just for storage traffic.
Yep.
They used 64-port 400G InfiniBand switches. Theoretically, this setup could scale to over 16,000 GPUs, though their actual deployment was just over 2,000.
It's still massive.
Oh yeah. Ideally, they picture future NICs having multiple physical ports, each connecting to a different plane. But the system sees it as one logical NIC that can handle packets arriving out of order from different planes. They mention InfiniBand Connect X8 supports 4 planes, for instance.
So what are the real wins with this multi-plane setup?
Several things. One, technically it's a type of multi-rail fat tree, so they could use existing software optimizations, like from NVIDIA's NCCL library. Two, it's cost-effective. You can connect many GPUs with just 2 layers of switches, making it competitive with other cost-focused topologies like SlimFly.
Cheaper network? Good.
3, traffic isolation. Congestion on one plane doesn't automatically spill over and mess up the others. That improves stability.
Nice.
4, lower latency compared to deeper 3-layer fat trees. And 5, if you have those multi-port NICs, you get robustness. One port or cable fails, the others keep working.
Any downsides mentioned?
The main one currently is that communication between planes still has to be forwarded within a server node, which adds a bit of latency. But they note that the better scale-up, scale-out convergence we talked about earlier could reduce that overhead in the future.
Okay. And how did it actually perform? Did they sacrifice speed for cost?
Apparently not. Their tests showed that the all-to-all communication performance, which is critical for MOE, was almost identical between their MPFT and a more traditional single-plane multi-rail setup. thanks largely to those NCCL optimizations.
Wow.
They measured really high bandwidth for the expert parallelism communication, over 40 gigabytes per second per GPU. And the bottom line, the final training throughput for DeepSeek v3 on the full 2048 GPU cluster was basically the same on MPFT as it would have been on the more conventional multi-rail network.
So, comparable performance but potentially cheaper and more scalable sounds like a win.
Seems that way.
Now, they also stressed low latency networks, especially for MoE. They compared InfiniBand, which they used, with RoCE, which is RDMA over Ethernet. What's the gist there?
Right. For those latency-sensitive MoE communications, both high bandwidth and low predictable latency are super important. InfiniBand generally wins on the latency front compared to RoCE.
Okay, InfiniBand is faster, latency-wise.
Typically, yes. But it comes with trade-offs. InfiniBand hardware is usually more expensive than Ethernet RoCE gear, and InfiniBand switches often have fewer ports per switch, which can make it harder or more costly to scale out to truly massive cluster sizes.
Ah, the classic performance versus cost scale dilemma.
Pretty much. You pay more for that lower latency.
So if RoCE is cheaper and potentially more scalable, did they suggest ways to make its latency better to make it more competitive for these AI workloads?
They did. Several concrete ideas. One, push for specialized low-latency RoCE switches, basically Ethernet switches stripped down and optimized purely for RDMA traffic.
That's the fat.
Exactly. Two, better routing policies. Standard Ethernet routing like ECMP isn't always great for AI traffic patterns. They advocate for adaptive routing capabilities in the switches to react to congestion dynamically.
Smarter traffic cops.
And three, improved congestion control and traffic isolation mechanisms within the RoCE. Switches themselves, things like virtual output queuing or more sophisticated algorithms to prevent traffic jams specific to these demanding workloads.
Make RoCE behave more like InfiniBand in the ways that matter for AI.
That seems to be the goal.
They also mentioned something specific to InfiniBand, GPU Direct Async, or IBGDA. What advantage does that offer?
Ah, yes. IBGDA is a cool optimization. It basically lets the GPU take over managing the control aspects of network communication directly instead of relying on the CPU to act as a middleman.
Cutting out the CPU proxy.
Right. For traditional setups, the CPU needs to be involved in setting up connections, posting work requests to the NIC, etc. IBGDA allows the GPU to handle more of that itself asynchronously. This significantly cuts down latency, especially when you're sending lots of small messages, which happens a lot in things like expert parallelism.
Streamlining the whole process.
Exactly. DeepSeek AI actually used IBGDA in their DeepEP library and reported substantial speedups. They argued this kind of capability should be more widely supported.
Makes sense. Okay, wrapping up, the paper touched on some broader themes too. Robustness, CPU issues, future trends. What were the final key takeaways?
On robustness, they flagged the real-world problems of network link failures, hardware dying, and even silent data corruption errors that don't get immediately flagged.
Which must be terrifying during a months-long training run.
Absolutely. So they push for hardware with better error detection and correction than just standard ECC memory, maybe built-in checksums, things like that, and better diagnostic tools for users to actually figure out what failed.
We need better failure analysis.
Definitely. Then, CPU bottlenecks. They reiterated that PCIe is often a limiting factor for getting data between the CPU and GPU quickly.
We talked about that with the KV cache.
Right. And they again advocated for direct CPU-GPU links like NVLink, or bringing the CPU into the same high-bandwidth scale-up domain as the GPUs. They also noted the sheer memory bandwidth needed by CPUs just to feed the GPUs over fast networks, and the importance of strong single-core CPU performance.
So the CPU still matters a lot, even in a GPU-dominated world.
It absolutely does.
And then looking further out, crystal ball time, future networks, and memory.
Yeah, they painted a picture of intelligent networks. Things like co-packaged optics integrating optical communication right onto the chip packages for massive bandwidth and better power efficiency.
Light-speed communication, literally.
Sort of. Lossless networks becoming standard, with smarter congestion control managed by the endpoints, adaptive routing being built in, better fault tolerance, dynamic resource allocation, basically networks that actively help manage complex AI workloads.
The network gets smarter.
And on the memory side, really interesting ideas. DRAM stacked accelerators putting memory right on top of the compute chip for ultra-high bandwidth and super low latency.
Stacking chips.
Yeah, they mentioned it could be especially good for MoE inference and the really far-out vision. System on wafer, or SOW, building almost an entire compute system on a single huge silicon wafer to maximize density and memory bandwidth for unimaginably large models.
Wow, sci-fi territory.
Getting closer. They also touched on tricky issues like memory ordering guarantees in these complex systems, proposing hardware solutions, and even doing computation inside the network itself or building in native support for compression formats like log-FMT.
Lots of exciting possibilities. So, okay, let's try and wrap this up. The big story from DeepSeek V3 seems to be this relentless focus on hardware-software co-design right from the start.
Absolutely. That's a core theme.
They innovated in the model itself with MLA for memory and MoE for compute efficiency. They leveraged techniques like FD8 training effectively. And they even engineered the network infrastructure with things like MPFT, all aimed at tackling memory, cost, and speed.
And importantly, they didn't just build it. They documented the challenges they hit with current hardware and proposed concrete improvements for the future. That benefits everyone.
It really does.
And I think what's really insightful here, for you listening, is realizing that understanding this interplay between the AI model and the hardware, it isn't just for the engineers.
Yeah. How so?
Well, it gives you valuable perspective on why AI is developing the way it is, why some models become more accessible than others, why inference speeds are getting better, hopefully. It helps you understand the roadmap, the potential, and the cost of future AI.
It really drives home that AI progress isn't just about algorithms in isolation. It's fundamentally tied to the physical machines, the hardware, that brings those algorithms to life.
Couldn't have said it better myself. Software ingenuity meets hardware reality.
So maybe here's a final thought for you, the listener, to chew on. We see AI models evolving at lightning speed, and the hardware is racing to keep up, and sometimes leapfrog ahead. What do you think the next big, maybe unexpected bottleneck will be? Or maybe the next big breakthrough that makes truly powerful AI accessible to everyone? Will it come from software cleverness we haven't even imagined yet? Or will it require another fundamental leap in hardware capability?
It's a fascinating balance to watch. Where will the next big constraint or innovation come from?
Definitely something to keep an eye on.